So this video is going to be on 3.2 properties of solids, and what we're going to talk about are types of solids and how their structure and composition account for their macroscopic properties. So what we're basically going to do is we're going to talk a little bit about what I introduced in Unit 2 about bondings and different types of compounds, and we're going to bridge that into this new idea of intermolecular forces and what we talked about in 3.1. So this is kind of like a review on top of adding a little bit of extra to our idea of what a solid is. So let's go ahead and kind of talk about properties of solids in general. And so when we're talking about solids, there are going to be very strong interactions between particles. Whatever that interaction is, it's holding those different molecules together really tightly. It's going to have a definite shape and volume, so it does not take the shape of the container like maybe a liquid would or a gas would. It has a definite shape and volume. It's going to be a regular crystalline structure, and the particles are going to be in a fixed arrangement. So they can't really slide past each other. And so what this is called is it just has a vibrational degree of freedom. So all it can really do is kind of vibrate right next to each other. And you see that in the picture in the right. So what are the different types of solids that we have? We're going to talk about 4 types of solids. And again, this should look familiar because we've already talked about these different types of compounds in Unit 2. The first compound we have is ionic. It's an ionic compound. It's going to be from a metal and a nonmetal, and this is going to be your typical salt. So NaCl would be your typical example. And when you're looking at the structures, all right, you're going to see this typical kind of crystalline structure here with alternating cations and anions. The second type that we're going to talk about is going to be a molecular compound. And again, this is going to be the non-ionic. So we're going to have covalently bonded compounds here. So what we're dealing with is generally going to be 2 nonmetals bonded together. Our typical example is going to be H2O or water, and you see this in the picture. The third example of a type of solid that we're going to talk about is metallic. An example of this would be aluminum. And we have a bunch of aluminum atoms here with those sea of electrons that we're going to talk about. And then the fourth type of solid that we have is going to be that covalent network. And we're going to explain the covalent network a little bit better than we did in Unit 2. I kind of introduced the idea. Now we're going to kind of look and delve into what a covalent network actually is and why it has the properties that it does. So let's go ahead and first talk about ionic solids. And for ionic solids, what it's going to do is it's going to be formed by a cation. So remember, that's a positive ion, and an anion, which is a negative ion. And each type is going to be surrounded by the other in a 3D lattice structure of varying shapes held together by lattice energy. And so we see this in the picture over here. So we have NaCl. And for NaCl, it's going to look like this, where we have 1 positive sodium for every 1 negative chlorine atom. And they're going to be held together by varying cations and anions, so that we have the negatives sitting next to our positive charged cations and vice versa. Down here, we have an example of a kind of more of a rhomboid shape for calcium fluoride, so CaF2. And so we see that calcium cation, okay, right here. And we have that fluorine anion sitting right next to it, and it's surrounding the calcium 2+. And so what you need to realize about ionic solids, and again, this is review, is that formula represents the ratio, okay, not ration, okay, ratio between ions, not discrete particles. And so, for example, the ratio for sodium chloride is 1 Na plus for every 1 chlorine. Or the ratio for calcium fluoride is 1 calcium for every 2 fluorides. This doesn't mean that there's only 1 sodium and 1 chlorine atom. What this means is it's just going to be a ratio. And so ionic solids, you get ratios. And so these generally are going to have really high melting points and boiling points due to the strong Coulombic attractions between the ions. What you have to realize is that the ionic bond that is forming, okay, these are attractions and they're going to be the strongest form of attraction that you can have. So that's why we see ionic solids having a really high melting point and boiling point. So if you try to melt sodium chloride or salt, it's going to take a while because the melting point is going to be really high. They're going to be brittle, and we're going to talk about this more on the next slide. And they're also really poor conductors of electricity in the solid state, okay, because they don't have free-floating charges that are able to kind of float around. But they're really good conductors when in liquid and aqueous form if they're soluble, because the ions can flow freely when they're in aqueous form. So they can conduct electricity really well. But again, really poor conductors when they're in the solid state, which is different, and how you can kind of tell metallic bonds versus ionic bonds apart when we're talking about solids. So now let's talk about why ionic solids are so brittle. So if we have this particular diagram right here, okay, and I labeled the atoms with our cations and anions, so positive and negative charges. And if you notice, okay, the positive charges are surrounded by the negative charges, and the negative charges are surrounded by the positive charges, because remember, opposite charges attract each other, and so this is what holds them together so well. However, if we put a mechanical force or a stress on this crystalline structure, and we kind of push the two sides apart, okay, like you would do if you're putting some kind of force on it, okay, you'll notice that the atoms kind of slip past each other. And so then what happens is we have this situation where we have two negatives sitting next to each other, two positives sitting next to each other. And so if we're looking at this right here and this right here, that is not going to be very stable because they don't like to be next to each other. And so what happens is there's an increased ionic repulsion, and so this repulsion ends up being a fracture. And so that's what causes ionic solids to be so brittle. It's because the particulate structure, the like charges don't like to be next to each other, and so they kind of fall apart. And so ionic solids are going to be brittle. Now, let's go ahead and talk about the second type of solids, and that the second type is going to be molecular solids. And so what you're going to see in the picture to the right is going to be dry ice. So this is going to be solid CO2. So if you get CO2 cold enough, all right, you're going to get dry ice, and this is going to be CO2. And the interesting thing about carbon dioxide is that it can sublimate, which means it can go straight from a solid to a gas. And you see that with dry ice. That's kind of like the wispy part of dry ice, is you see it going from a solid to a gas, because it doesn't have a very high vapor point. So these are going to be formed by distinct individual neutral molecules, which in turn form molecular lattice structures. And so this is a little bit different than ionic solids, where you had kind of that ratio of ions. Okay, these are distinct neutral molecules. And they're going to be formed exclusively from non-metal atoms, so on the right of the periodic table. And the chemical formula is going to represent the actual number of atoms in each individual molecule. It's not like the ionic solids where you were dealing with ratios. These are the actual number of atoms in each individual molecule. So for CO2, we have 1 carbon for every 2 oxygens for each individual CO2 molecule. They're going to have relatively low melting and boiling points because of the weak intermolecular forces holding the molecules together. So all we have going on holding these molecules together is going to be the London dispersion forces for CO2, because CO2 is a nonpolar molecule. And it's not a very big molecule, so those London dispersion forces are not very strong. And so this is what's causing the relatively low melting and boiling points that you see with molecular solids in comparison to ionic solids. And also, they're going to be really poor conductors of electricity in all states. even if they're soluble in water, because those electrons are held really tightly in those covalent bonds. They're stuck in the covalent bonds, and so they can't flow freely, and you need a free-flowing electrons to be able to conduct electricity. So you're going to see poor conductors of electricity in all forms. So now here are some examples of molecular solids. And so the first example that we see on the left is going to be iodine. So that's a picture of solid iodine and a particulate diagram of solid iodine. And basically, it could be structures like iodine, it could be O2, it could be S8. And we see that the nonpolar, okay, these are all nonpolar atoms, okay, they're only really held together by those weak London dispersion forces. And so they don't really hold together all that well, so you're going to, again, see that low melting and boiling point. The example on the right is going to be benzene. Again, you see those distinct molecules that are held together. Weakly, benzene is going to be nonpolar as well, and so again, London dispersion forces are holding them together, which is why you see those low melting and boiling points. So now, the third type of solid that we're going to talk about is the covalent network solids. Now, they're not super common. The most common ones you're going to find is the carbon covalent network solids, so your diamond and your graphite. You could also have silicon dioxide, which is going to just be basically sand that you could see on the AP exam. They do tend to have one covalent network question on the AP exam for some reason. They like covalent network solids because they're different. It's not necessarily an exception to a rule, but they are different. And so here, they're going to be formed by distinct atoms, and they're all going to be bonded together covalently in a 3D network. So what we're seeing on the right, the picture that's kind of moving and rotating around, is we have a bunch of carbon atoms, and they are kind of covalently stuck together to form this like kind of large network. And what we're looking at is we're actually looking at what the structure of a diamond looks like. And so they could be formed by carbon, most of the time they're carbon, or other metalloids. So you could see silicone, you could see germanium, you could see boron. So the metalloids, the ones that are going to be between your metals and your nonmetals at that staircase in the periodic table, those are what's going to form your covalent network solids. And so these have really high melting points and hardness, especially for covalent compounds, because remember, covalent solids, okay, they have fairly low melting points. But these are going to have really high melting points, and they're going to be really hard. The hardest thing that we can use is a diamond. So they're really, really hard. And they're really poor conductors of electricity because those electrons are, again, still held tightly in those covalent bonds. Examples that you could see on the test: carbon, okay, diamond and graphite, or silicon dioxide, a silicon and carbon covalent network, a germanium and arsenic. You could see a couple of different ones, but I would bet on it being something to do with carbon or silicon dioxide. Those are the two common ones. And so when I say that they're really hard, I'm talking about diamond. You should be very familiar with graphite. You are probably all writing with graphite right now, okay? Graphite is lead in your pencil. And you might be thinking, well, my lead in my pencil isn't super hard. And you would be correct. That's because it's a slightly different structure that we see. And so carbon in graphite form is sp2 hybridized, which is really interesting. And so what they're going to do is they're going to form really large sheets of carbon atoms in a trigonal planar arrangement. And so what's happening with your lead pencil, and why you can write and kind of rub off that lead onto the paper so that you can see your words that you're writing, is that these sheets can slide against each other and kind of slide off. So instead of breaking up those sheets, what you're doing is you're kind of sliding a sheet off. And they have weak intermolecular forces that hold the sheets together. And so that's what you're breaking when you're kind of sliding that pencil along the paper. You're kind of sliding the graphite sheets past each other. Now, interestingly, graphite is a really excellent conductor of electricity because it has delocalized electrons that can flow across the graphite sheets. And you can see this in the picture. And so here's another picture of that idea. Okay, so we have the sp2 hybridization. And again, I don't foresee this being on the AP test, but they could for some reason ask you. So I'm showing you a picture of it. But because each carbon atom has a sp2 hybridization, the unhybridized p orbitals align with the adjacent carbon atoms. So you see that in this kind of a middle picture right here. You have your sp2 hybridization, and the loops are your unhybridized p orbitals. And so they line up with your adjacent layers, and that's what kind of holds them together and allows those electrons to kind of freely flow between them. And so again, that delocalized electrons allows the allows it to be a good conductor of electricity because of those p orbitals are letting those electrons kind of flow between the carbon atoms. All right, and last but not least, we have metallic solids. If in the picture, you're going to see that sea of electrons that we talked about in Unit 2. They're going to be formed by metallic elements, and they are going to exhibit metallic bonding where valence electrons are free to flow from atom to atom. So again, that sea of electron model, you can use that in any FRQ if you're trying to explain the properties of metallic solids. They are great conductors of heat and electricity because those electrons can flow freely. This is why you use iron or metal pans for cooking, so that it can transfer that heat into the food that you're cooking. This is why we use metal for wires when we're running electricity through things. Okay, it is very malleable and ductile, and the melting points are going to vary depending on the metal, but generally speaking, they are going to be fairly high. The difference here is that they are great conductors of electricity in solid form. All right, so if you're trying to compare ionic and metallic solids and figure out which one it is, okay, they're both melting points are going to be kind of high, but you're going to look at the conductor as a solid versus a conductor as an aqueous solution. Okay, your aqueous solution conductors are going to be your ionics, and your metallic solids are going to be good conductors as a solid, and they aren't going to be soluble in water, so you're not going to have an aqueous solution to deal with. So let's go ahead and talk about how we would identify the types of solid by its formula. So I have 6 here. Go ahead, pause, and see if you can figure out what types of solids each of these are based on the formulas. All right. So this first one right here, if it doesn't look familiar, it should kind of trigger your memory a little bit. We have talked about this before, but this is actually sucrose. It is a sugar, all right? And if we're dealing with carbon, hydrogen, and oxygen, okay, all of those are nonmetals. And so that should trigger you to be thinking this is going to be a molecular solid, all right? SiO2. That's one of the examples that I gave for something specific, but that silicone should kind of give you a hint that it is a metalloid, and so maybe something interesting is going on. This is actually a covalent network solid. Okay, MgSO4 is interesting, all right? We haven't done polyatomic ions yet. I haven't given you the list to memorize. But SO4 is a polyatomic ion, which means it's going to be an ion, so it is going to be a charged, and it's actually a 2 negative charge. Mg you should recognize as an alkali earth metal. It's in group 2. It's going to be a 2+ charge. So we're dealing with ions here, so this is going to be an ionic solid. CO2, again, nonpolar to nonmetals, so that's going to be a molecular solid. NaF, we have a metal and a nonmetal. That should point you in the direction of ionic. And calcium by itself, calcium is a metal, and so if we just have a calcium solid, it is going to be a metallic solid. And so when you are kind of looking at these, that's kind of like the method that you need to use. Okay, so what type of atoms are they? If you look at your periodic table, you should know, okay, what are nonmetals, what are metalloids, what are metals, just quickly, so you can kind of use that method to figure out what types of solids they are. Once you figure out what type of solids they are, then you can kind of predict what's going on with the melting point, with the boiling point, what type of intermolecular attractions they're going to have, and you can predict properties as well. So let's go ahead and go over a couple of practice problems. So here's the first one. Which of the following should be the identity of a white crystalline solid that exhibits the following properties? So it melts at 360 degrees Celsius. It does not conduct electricity as a solid. It does conduct electricity as an aqueous solution. All right, that last bullet point should key you in. If it conducts electricity in an aqueous solution, we are looking for something that is going to be ionic. So immediately ionic from that last bullet point. So if we look at A again is sucrose. Those are all nonmetals. I'm not getting ionic there. That's going to be a molecular solid, so it's not going to be A. I can kind of cancel that out. KOH, so hydroxide. The OH is a polyatomic ion that's going to have a 1 negative charge, and that potassium is a metal, so I have a metal and a non-metal kind of group there, so I'm thinking maybe that's the right answer, but let's go ahead and double check. C is a diamond, a carbon, that's a covalent network. Ag is silver, that is going to be gold. Nope, I was right, that's silver. That's going to be a metal anyways, regardless of what it is, so that's going to be a metallic. So I can cancel out C and D, and we're going to go with answer B. It's the only ionic solid that we have for our answer choices. So let's go ahead and go through that in words. A is a molecular and it couldn't conduct electricity. C is covalent network solid. Melting point would be much higher and does not conduct electricity. And then D is a metal and would conduct electricity as a solid, but not soluble in water. So the only one left that we have to choose from is B. All right, here's another question. Which of the following diagrams best illustrates how a metallic solid is malleable after displacement? So first off, we have to make sure we understand the word malleable, and malleable just means that it's able to kind of bend into different shapes. And so we're trying to figure out how metals are able to bend. Well, first you have to realize that what's going on in a metallic bond is that you have that sea of electrons. And so for right away, the only one that looks like it has sea of electrons for me is C. So I'm assuming that that's what the answer is going to be. But I'm going to go ahead and explain all of the answer choices. But I'm going to go ahead and make a circle on C because I'm pretty sure that's the right answer. It's the only one with the sea of electrons. If we look at A, we have this negative, we have a positive and a negative, so we have the negative charge, we have the positive charge, and after displacement, we have a positive charge right next to a positive charge, and so what's going to happen here is that's going to fracture, and this is why ionic compounds are so brittle, and so this one is an example of ionic, and this is why they are brittle. All right, that is not malleable. Because it's going to fracture, it's going to kind of break right here because it's not going to like to be next to the same charges. For B, we got something weird going on. I don't really know. We have positive charges, we have negative charges, and then we have this weird like -2 charge going on down here. I'm not sure really what's going on. We lost one charge and they kind of combined. So I'm going to say no to that one because I don't even know what would cause that. And then D here, this looks like a covalent compound. We have one bigger atom, and it's bonded to these 3 smaller atoms here, and it looks like they're kind of in a kind of in a line. I'm thinking this is like a polymer, maybe like a rubber or something like that, where it can kind of bend and take different shapes. So this one is kind of a good distractor, because it does look like it's kind of malleable, because it's kind of bending like you would think like something malleable would. But the way that it's drawn, it's more of a covalent compound than anything else. So C is going to be our best answer, because we can see that sea of electrons. Okay, we see the electrons like kind of like floating around here, and then after displacement we can kind of see it kind of like in a different shape here, but still you could tell that sea of electrons is still free flowing, and it hasn't like really fractured at all. And so C is going to be your best answer there. All right, last example. A student finds a bottle of magnesium chloride, or MgCl2, and hypothesizes that the solid is a good conductor of electricity because it contains magnesium, which is a metal, and all metals are good conductors. Do you agree or disagree with the student and justify your claim? Well, let's think about this. So if we just had magnesium, he would be correct, because metals are very good conductors, but he doesn't just have magnesium, and you can't split something and not take into account the entire molecule. So if we look at this whole thing, we're dealing with MgCl2, and if you think about it, Mg is a metal, Cl is a non-metal, so this is going to form an ionic compound. And what do you know about ionic compounds is that they are not good conductors in solid form, because those charges cannot freely flow. They are very good conductors in aqueous solution though. But this is asking, is this saying good conductors in solid form because they have a bottle of magnesium chloride and hypothesizes that the solid is a good conductor? So I am going to have to disagree with this guy. All right. If we disagree, okay, and the reason why is solid magnesium chloride is not a good conductor of electricity because its ions are unable to flow freely. The magnesium is a cation in this compound, and it's rigidly bonded in an ionic lattice, so it does not exhibit the conductive properties that neutral magnesium metal does. All right, so you have to explain like it's ionic, and so the ions are not able to flow freely, in contrast to if it was just magnesium, where it would be able to flow freely because it would be in a metal form. All right, and that is it for 3.2.